All right, let's check out, excuse me, problem number 4. This is welcome to my house. I'm not at school anymore. All right, so number 4, we're looking at a whole bunch of different scenarios here, right? We have charge A, charge B, charge C, and charge D. And we have a whole bunch of different interactions, right? So we know we put a test charge T at each one, and we have the reaction or the force that T feels, right? In case A, we have a strong attraction. In case B, we have a strong repulsion. In case C, we have a weak attraction. And in case D, we have another strong attraction. All right, and then we're going to be looking at what are the interactions between these particles, right? We want to see what their interaction is going to be. So before we get too far, I want to just take a second and kind of decide, well, what are the possibilities, right? What could A, B, C, and D, what could their charges be? So if we look at A, right, what are the possibilities if we have a strong attraction between a test charge, a positive test charge, I think. So ABC, T to Q, cosine 0. Positive test charge T. Yeah, so it's a positive test charge. Okay, so if we get a strong attraction, right, and it says they're all plastic, which means they are all insulators, right? Or A, B, and C are plastic. D is copper, so D is an insulator or a conductor, but A, B, and C are insulators. So if we have a strong attraction between A and our test particle, right, and we know A is an insulator because it's plastic, right, the only possibility for A, because it's an insulator, which means if it had an induced charge, it would be a weak charge or a weak attraction, right? The only possibility for A is that A is negative. A has to be negative because it's an insulator and because it's attracting a strong attraction to our positive test charge, right? And that's the only kind of case that we could have where we get a strong attraction with an insulator. If we look at B, right, possibilities for B, I guess we know it's minus Q, right? It says it's minus Q. B, right, possibilities for B. Well, B, we get a repulsion between B and the test charge. The only time we can have a repulsion, right, regardless of insulator or conductor, is if the charges are like, right? You don't get induced repulsions. You only get induced attractions. So we get repulsion, which means B has to be the same charge as the test charge, which means B is positive. And it's plus Q. C, we get a weak attraction. Now, because C is an insulator, right, if we have a weak attraction, that means that C has to be neutral, right? C has to be neutral because it's giving us a weak attraction. If it was charged, then it would give a strong attraction or a repulsion, right? But because it's not giving a strong attraction or a strong repulsion, it's giving a weak attraction, it has to be neutral, and its charge is 0. And D is the interesting case here because it says D is a it tells us that D is an uncharged copper ball. So D is neutral. It's just copper. All right, and we get a strong attraction for D because it's a conductor, right? It's copper, it's a conductor, and conductors can create strong attractions with test particles, right? Because they're easy to polarize. It's like question number 1, where we had the conductive rod, right? It created a strong attraction. So here, like we've gone through, we know what each of the charges are now, right? We know A has to be negative because it created a strong attraction. We know B has to be positive because it created a strong repulsion. We know C has to be neutral because it created a weak attraction, and it tells us that D is neutral. It's an uncharged copper ball, right? If we didn't know, if it didn't say that D was neutral, we wouldn't know if D was charged or uncharged, right? Because there's two cases, right? We could, for conductors at least, D could be uncharged but be polarized and creating a strong attraction, or it could be charged and still create a strong attraction, right? So D we wouldn't have been sure of, except that they told us that D was neutrally charged or uncharged. All right, so part A, what is the nature, I'm drawing all over the place. What is the nature of the force between A and B? Well, it's part A. If we look at A and B, A is negative, B is positive, so we should get an attraction. And because they're both charged, it should be a strong attraction. Right? I mean, it doesn't ask us to specify whether it's strong or weak. It just says attractive or repulsive. So we say it's attractive. Nature of the force between A and C. So A we know is negative. C we know is a neutral, and we specify that this is an insulator. Whereas this is a neutral conductor. So if we're talking about A and C, right, a charged particle and a neutral insulator, we will get, this is part B, a weak attraction. Right, so for insulators, when insulators are brought near charged objects, we get attraction, but it's going to be weak because those electrons can't move around to reorient themselves, right? All they can do is kind of shift and become polarized. We get a weak attraction. So choices here, right? It says attractive equal to A and B. It's not going to be equal to A and B because the A and B attraction is strong and it's weak. So it's an attractive force that is smaller than the magnitude between A and B. Boom, 2 for 2. I'm on a roll. C. C, we want to know the nature of the force between A and D. So if we look at A and D, we have a charged particle, negatively charged, and a neutral conductor. Because it's a conductor, we're going to get, well, first, because it's neutral, we'll get attraction again, right? And then because it's a conductor, it's going to be strong. Now, strong is kind of a tricky one in here, because is it as strong as the attraction between A and B, which are both charged? Probably not. Is it definitely stronger than the charge or the attraction between A and C, where C is a neutral insulator? For sure. But it doesn't ask us that. It just asks, is it attractive or repulsive? It's definitely going to be attractive because it's neutral, right? Anytime we have neutral, we're going to get an attraction. We can't have repulsive when we're working with neutral things. Part D, I'm running out of space. What is the nature of force between balls C and D? So C and D are both neutral. If we bring two neutral things together, we get nothing. No interaction. Right? They're not going to attract. They're not going to repel. They don't have charge to force the other one to polarize or to be induced to charge. So we have no interaction. So for D, when we look at two things that are both neutral, we're going to get something where we don't get an attractive or a repulsive force. Boom. Correct, 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 correct. And, you know, 4 for 4. It's what I do. How do I get out of here? This is always the hardest part for me, because I have to like move the mouse around the screen until the little button comes up that lets me stop the recording. And there it is. I finally got it. Whew. Thought we were gonna